Hi everyone. In this section I'll be looking at graphical summaries. Once again we'll start with the outcomes. Most important, know the definitions, then state the purpose of graphical summaries, identify which graphical methods is best suited for which types of data. Now you should recall there is a lesson on the different types of data because I stressed in there that the type of data will determine how we analyze the data and also how we summarize the data. And then, really very important, is extracting information from graphical summaries. Now you'll see I don't have in here constructing the actual graphical summaries, constructing the charts. And the main reason for that is because everything is done via software. However, the information that you should be able to extract from the graphical summaries is not done by software. So you should be able to do that. So the focus is more on extracting information than what it is on constructing the actual charts. Right, now the first one that I want to mention is a very obvious one, which is tables. Now that's usually one of the first things that we do with data that we collect, the raw data, is we organize it into a table. Now there's only one rule to follow with the table, and that is to keep the table simple. Don't make it cluttered, don't try and add too much information, rather split it up into 2 or 3 tables, because the whole purpose of summarizing data, whether it's tables or whether it's graphically with charts, is to make it easily readable. So the reader should be able to easily extract information from the summary. Whereas if it's too cluttered and complex, then it defeats the purpose of the summary. One of the first charts is the pie chart, which you should have encountered by now. It's very simple. We have 360 degrees in our circle, and we take the ratio for the different categories and we work out the degrees that each category will represent in our chart. Important to have a heading and also to have a key or a legend. Now, when it comes to the actual uses, then obviously a pie chart divides the total into different components. So here I have a total of 2,400. Right, this is the number of registered students every year for 4 years. So in 1988 we had 2,400 split between 3 faculties, and this is how that division looks like. Right, those 3 components. Now the pie chart allows us to easily compare the components to the total. So we can see here this takes up almost half of the entire total, whereas this takes up a quarter of the total. Disadvantages is it can display only one variable at a time. So we can only look, for example, at 1988. We can't have one pie chart where we are comparing 1988 to any of the other years. And then also it is not suitable to compare the components to each other. If we want to compare, then we should have these percentages present. But if we don't have these percentages or some indication of the size present, then it will be very difficult to distinguish between the different components in some cases. And then of course, lastly, this is really only suitable for qualitative data. Right, so not quantitative. Qualitative, like we have over here, we have labels, nothing is really being measured as such. Right, the one that is most useful compared to the pie chart is actually a simple bar chart. Now, a simple bar chart allows us, unfortunately, only again to compare one set of data. So in this case, I'm comparing the totals for every year. However, we could have compared the number of students within a year, but we won't be able to compare between the years, not for a simple bar chart. So here, it makes it very easy to compare between the different components. Right, we can clearly see where differences are, but it makes it a bit difficult to compare each component to the overall total. To get that, we need to add all of these bars together, which is not that easy if we just quickly want to extract some information from the graph. Right, the next one is an extension of the simple bar. This is the multiple bar. So now we're actually including more variables. Right, we're looking at the different years and we're looking at the different faculties, and we're able to compare very easily. Now this one looks at the actual numbers, the frequencies. So it's very easy to compare. If we color code it nicely, then we can compare between the different years for each faculty. We can also compare between the faculties for every year and between the different years. The nice thing about this is it will allow us to also detect any trends and associations. Now this comes up a lot when we perform chi-square tests of association. The next one is a component, or the stacked bar, which is very similar to the previous one, the multiple bar, but here we're stacking the bars on top of each other. So it has pretty much the same interpretation as the previous one. Here, the main advantage though is it's very easy to compare each component to its overall total, like with a pie chart, because now all the bars are stacked on top of each other, so we can see exactly what the total is. By adding these lines, we can also see what the trends are. But the percentage component chart is a little bit more difficult to read. Over here we have 100%, which means we've converted the totals to 100%, and we've calculated the percentage of each component out of that total. Now the labels that I'm using here are the actual frequencies, so we'll have to read the percentages from here, and that's where it becomes a bit difficult, because now we can see that the 600 is almost 50%, but what is 230? We're going to have to look at what is the top of 230, which seems to be like about 67 around there, and then subtract something which looks to be like maybe 48. So we can see that to get the actual size percentage wise for these other bars on top of the bottom one, it becomes a bit difficult. We also don't know what the actual totals are over here because we're working with 100%. So it's very difficult to compare the actual components to each other because of the changing totals. So I would advise that you practice interpreting this bar a bit with the quiz following. Right, the next one is a Pareto chart, which is named after an Italian economist. It consists of two components. First will be the bars, right, the simple bar chart, and you'll notice that it is arranged in descending order. Here we have the actual data set, or the actual table, and it is not arranged in any specific order. But on the graph, the bars are arranged in descending order, and the line is cumulative. Okay, the line chart, that's cumulative, which simply means that the first one will start with whatever value this first bar is, which is 51, the highest bar. You can see here coal, highest bar is 51, and then we'll add 21 to it. So it's 51 plus 21, which gives us 72. Then we'll take this 72, we'll add 16 to it, which gives us the 88. So by the time we get to the last one over here, we will have the total of 100. So this just allows us to see in a different way how the changes take place with these bars. Right, the next one is called a dot plot. Now it is exactly what the name says. If we take, for example, the number of vehicles for 20 households, then the first step will be to find the minimum, the number of vehicles, and then the maximum number of vehicles, indicated on my dot plot on the number line 0 and 4, and then obviously all other values will be in between, and then we just make dots wherever the value should be. So 3 means that we'll make a dot at 3. There's another 3, so we'll make a dot above the first one, also at 3. Now this is really only useful for small samples, and in a later example we'll see why, and also small ranges. In other words, there shouldn't be a big difference between the minimum and the maximum. If those conditions are satisfied, like small samples and small ranges, and in this case discrete data, then it actually is a very useful plot to detect patterns in data sets. You can see here I just added the line to give us an indication of how the data is distributed. Right, now the next one is what we call a stem and leaf plot, which is also a very useful one. In this case we have 12 race times of athletes, and you'll see that it has decimal places. So the first thing with our stem and leaf plot is that we have to create a dividing line between the stem and the leaf. Now this dividing line, like I said, separates the stem and the leaf, and in our case I will let the line represent the decimal point. So that means if I take the first value here, 12.2, then my key will say 12.2 will be 12 line 2. Okay, so the decimal point is represented by this line. So that means on the left by the stem, I will have the values 12 to 17 because the smallest integer I have is 12 and the largest integer I have is 17. So that will be my stem, the integer part. It's the integer part for this example. It doesn't always have to be like this. Right, now you'll see automatically with the stem and leaf, we start with the smallest, we end with the largest integer. So the data is arranged in ascending order from smallest to largest. Next, we start adding the leaf part. So 12.2 will have 12 as an integer and 0.2 as a decimal. Because the line represents the decimal point, we'll just write a 2 on the other side. The next one is 14.1, 14.2, 14.4. So we have 1, 2, and 4. So we'll read this as 14.1, 14.2, and 14.4. We always have the leaf going from left to right, small to large. Okay, so for the stem, at the top the smallest, bottom the largest. For the leaf, left to right, small to large. You'll also notice that there's no 13 in our data set, but we still write 13 over here on the stem part. We just exclude the leaf. Don't put a 0 because that means 13.0, which is just 13, which means that there is a number 13 in the data set, but there isn't, so we just leave it blank. Now, same as before with a dot plot, this is very useful to see the spread of the data, right? The pattern of the data. It also arranges the data in ascending order, so we can actually find some other statistics from this data set, which we'll look at under numerical summaries. Right, the next one is our line graphs. Now, line graphs can be very useful. It usually helps us to detect patterns over time. So usually a line graph will have time, whether it's minutes, seconds, days, months, years, doesn't matter. It will have that on the x-axis from left to right, small to large, and then we'll just connect the dots with our line so that we can actually see the pattern that we have in the data. We can have multiple line like this one. We have 2 lines, which allows us to compare different patterns as well. Right, then the last one is a scatter plot. Now this is for bivariate data. Remember bivariate data, if you look on the section on types of data, the bivariate data means that we have 2 measurements for every element in our sample. So we have 2 variables describing, or 2 characteristics describing each element. In this case, it's the weight and the height. Now what makes this example nice is that a third variable is actually included in here, which is a dichotomous variable. Dichotomous just means 2 possibilities. So in this case, female and male, it's color coded so we can see the weight and the height for the females compared to the males. Right, now I want to end with a note on scales. If you look at the heading here, this was data collected from a survey, and it was regarding online shopping habits. So we asked females and males how frequently they shop online, and these were the responses. Now this data set, as it is here, right, the table, was entered into Excel, and Excel was used to generate this graph. Now this graph was not manipulated in any way. It is the first automatically generated graph that Excel gave for this table. And at a first glance, it seems as though over here the males is a little bit more than the females regarding never shopping online. And it seems to be a pattern, right, where the females or where the males are the smallest percentage, and then it increased to the largest percentage. Okay, now remember graphical summaries, it should allow us to extract the information at a glance. However, at a closer look, we will see that this starts at 75%. So that makes this graph completely misleading. And as I said, this is actually the standard graph that Excel generated without being adjusted. If we were to adjust the scale on the y-axis to make it start at 0, then we get a true reflection of what the data actually says. So although the percentage of males increase regarding the shopping habit, it is still not nearly as large as the females. It makes up a very, very small percentage. Right, now this last bit is really important because we always need to have a look at the graphs that are generated automatically and see whether they are really representing the data like they should. If not, we just make a slight adjustment, like was done in this case, so that we can get a true reflection of the data.